Select the major product of the following reaction. So in order to decide the major product, we need to examine our starting material and what we're reacting it with and determine what sort of reaction this is. So if you look at our starting material, we have a halogen, which is a good leaving group, that is on a secondary carbon. And that secondary carbon happens to have a benzene ring as one of its substituents. So this is a secondary benzylic halide. And so the sort of reactions that we have seen for alkyl halides so far, including benzylic halides, are substitution and elimination reactions. And those both can occur because your halogen, as long as you're not looking at a fluoride, is a good leaving group. And so when you do a substitution or an elimination, you're going to push off that leaving group. So with a secondary benzylic halide, we want to think about what are the possible substitution and elimination pathways. So secondary alkyl halides can undergo SN2 reactions, and because this is benzylic and your carbocation be resonance stabilized, they can also undergo SN1. So we could have either SN1 or SN2. And in terms of elimination pathways, you could also have either of the two elimination pathways. It could be either E1 or E2. So that really didn't narrow things down. We're going to need to look at what we're reacting it with. So we see that we have sodium ethoxide. So remember, whenever you see a sodium in front of something, sodium is positively charged. Whatever is next to it is a negative charge. And we're looking at an ionic bond here rather than a covalent bond. So we have sodium ethoxide. So that ethoxide is really what our reagent is. The sodium is a counter ion. So this ethoxide is what we're considering. This is a strong base. It's also a strong nucleophile. So this could undergo either a substitution or elimination depending on the substrate structure. So seeing that this is secondary, it's going to be more prone to be an elimination reaction than a substitution reaction. If that were a primary halide, you'd be looking more towards SN2, the substitution. But since it's secondary, we're looking at an elimination reaction. So specifically an E2 elimination. So with our E2, that's the concerted elimination, our leaving group and the beta hydrogen that we're going to eliminate need to be 180 degrees apart from each other. So we need to look for hydrogens on our substrate that are beta to that leaving group and also 180 degrees apart. And just to quickly show the mechanism, using a generic base, that base would abstract the hydrogen, the electrons from the carbon-hydrogen bond form the alkene, and then you push off the leaving group. So here is our alpha carbon. So there's our leaving group, and you're gonna look for beta hydrogen. So we don't have any there on the benzene ring because we can see the 4 bonds to that carbon, but we do have 2 here. And so with our E2 reaction, we've got 2 different hydrogens we can take, but we also want to recognize we want to form the most stable alkene that we can form, right? So we're looking to form the most stable possible alkene. So right now this is lined up, so this hydrogen on the dash bond is 180 degrees away from the bromine. A bond rotation, right, and there's free rotation here, would spin that around so we could eliminate the other hydrogen. So we're making the alkene here, so you want to think about what that alkene is going to be, and it's going to be di-substituted. So we know that we could either form a cis or a trans alkene, and hopefully remember that the trans alkene is more stable. So even with just that, we might be able to now say, okay, we're looking at this trans alkene, but I am going to keep going and draw this product, the mechanism and the product for you. Okay, so there is our base, our ethoxide. So it can remove that hydrogen that is 180 degrees away from the leaving group. The bond to the phenyl ring is pointing down and the bond to the methyl group is pointing up. So they're pointing in opposite directions. That's how we get the trans orientation here. So the key is that the benzene ring and the methyl group are pointing in opposite directions. It doesn't have to be down and up. It could also be flipped. In this case, it is drawn, so it's pretty clear from the structure. So then we can break this carbon-hydrogen bond. Those electrons come in to form the alkene, and you push off the bromine. Okay, so we are selecting to form the trans alkene because that is the more stable alkene, and so that's what's going to be thermodynamically favored. As a minor product, you probably would remove some of that other hydrogen, which would give you the cis-alkene, but the major product would be the trans-alkene. So this is an example of a stereoselective reaction. It selects for the most stable stereoisomer of the product.